Now, I have made videos on batteries, and I have made some videos on hydrogen, and I've got things wrong. And I'm embarrassed a little bit. And I am trying to make this video finally to not just BS about is can batteries be cost effective or are they not? I'm and show some mechanics. I want to finally get some stupid answers to these questions. And oh, this is the hydrogen one. That's my next video. Okay, and I'm going to go through some PowerPoint slides and work through issues with batteries. Now, this it kind of drives me nuts that these people say, oh, there's all this different blah, 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 batteries to back up distribution systems, batteries to have a microgrid, batteries to have frequency regulations, batteries to support this or that. And then the World Bank says, oh, you can use batteries for load shifting, firm capacity, and all of this stuff. And I just think there are two cases. I could be wrong, and you can't overlap something. They're basically batteries for ancillary services, and I call this the firehouse case, where you have these ready to support fires, not really fires, but sudden things that happen. And then they're really batteries for shifting around the load. I don't know why I put this in. So this is my battery example, my firehouse example here of people in a firehouse. They're sitting around. And they sit around most of the time, just like batteries would sit around most of the time, except suddenly you run out of power, suddenly you need the frequency gets out of hand, suddenly your loads, suddenly clouds come over your solar, and your solar isn't producing, and you can't get the rest of the ramp up in your other plants ready. Suddenly things happen, and you have to have the batteries ready to go. That's ancillary services. And that's very interesting. I'm going to talk about moving batteries from one period to the other, storage. Okay, and you can find all this stuff, and are batteries really economic? This is my water tower thing that I'm sick of. I almost like this one a little better. This is accumulation of storage in a warehouse, and this is moving things in and out. And we're going to make a little example today, if I can make this video. Oh, God, I hope I can. Finally, of how fast you can move things in and out. That's what I call the capacity, and how much area you have to store it. And as you uh, uh, understand, and as I'm going to go through, batteries depend on both things. In this case, it's my water tower case with the capacity, and this is the storage. I don't know which is a better example, and this is fascinating to me that the batteries for a car need to charge so fast, and you take this ratio of how much energy you have to how many kilowatts you have, and what I normally do is say, well, if I take kilowatt hours divided by kilowatt, that gives you hours, and I call that the duration. So this is, in this case, hundreds of megawatts, thousands of megawatt hours. That's 10 hours. This one, it's less than an hour. This one in your battery, it could be 1 hour. So 1 hour of storage gives you 1 hour of capacity, blah, blah, blah. No, I shouldn't say blah, blah, blah like that, maybe. This, I don't know. This is some home storage system or something, maybe. And then we could, if we have 15 hours of storage for 3 hours, we get 5 hours of storage. But it's not really good to call it hours like that necessarily, because things can move up and down, and we have to be a little bit more careful with getting off track with some of this stuff. I've probably done this before, but this is batteries for ancillary services, and this shows a example of what you find on the internet. AES developed a system, and it's at 2 megawatts, 500 kilowatt hours. Ooh, that's only 15 minutes of storage. And maybe in there are pictures, and they were bragging about it. And they say, this is the greatest thing. We made this, and we can really make batteries work. But that must be battery for ancillary services, because if we're going to store power from the sunlight during the day and use it for people reading during the night, we're going to have to do something else. Here's some more pictures. And here for me is the big elephant in the room. And it should be obvious. Now I'm going to make an example of storage over one day. But of course, solar, you can have clouds for 3 days and then you'll run out. Or the load's going to be different on a Sunday than another day, and you're going to run out. So the real issue with storage, or the summer versus the winter, of course that's the issue. Please don't, just because we're studying it for one day, that doesn't mean we don't understand that there's this gigantic issue around batteries. Okay, and I had to study, how you can get the capacity. Whenever we say capacity for a battery, it's the discharge, not the charge. And you can take the amps and multiply by the voltage and get the number. Okay, so what I'm going to do today is work through some storage issues and try to show you some real numbers rather than just the BS, hopefully, and BS coming from me as well. And my big question is, can we? The battery cost is declining. We all know this. We've seen this Bloomberg thing over and over and over again. If it's Bloomberg, God, it must be right. Bloomberg, blah, 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 blah. He's a billionaire. Okay. Well, maybe he's right. But this battery, is this just the battery cost? What does this mean? What's the true cost of batteries? How much does it have to come down? And what we find is the battery cost has a lot of other things now. These adders kind of drive me nuts. The margins for everybody needs to get their margins. Everybody needs to get their profits. That's all people seem to talk about. But we do have a difference between a battery that has a 4-hour duration. And remember, that's just dividing the kilowatt hours by the kilowatts. It doesn't really necessarily mean that you have to wait 4 hours of storage, and I want to show you that. And then we I don't know, they put the different prices, and this battery with 4 hours per kilowatt hour, not per kilowatt, per kilowatt hour of the storage amount. Remember, this is this number. This is this number per kilowatt hour. They give you a number. Okay, now I had to go to my elementary school to remember how to make this work. If we have a different battery, and we start with all this stuff, and we add it all up, and oh my God, developer margin, developer overheads, EPC margin, oh geez. We get from this to this. Okay, maybe we could take this one and compare just the battery rack and the balance of the system, and then we got to add all this stuff up. Unfortunately, different countries, I think, will have different adders, but I'm going to use these. And so if we have a 1 hour duration, the battery cost will be less, but the cost per kilowatt hour will be more. And so you can just take this versus this and this versus this and get a little slope and intercept and get a little equation that says, okay, if this is an equation where y is the cost of the batteries and x is the duration, the slope of the cost versus the hours as you have more and more hours, you get less cost per kilowatt hour. I should have written this down, shouldn't I? And then the intercept here is 601, so I suppose that's if there's a zero duration, which there isn't such a thing, but you can do that. And then I'm skipping this one. There's another thing that shows how the costs go down. And then we get our different, somebody actually did this. Now, you've got to be, somebody made an error, I think, because the cost per, oh no, this is the cost per kilowatt. Excuse me, they didn't do it wrong. The cost per kilowatt goes up as you have more storage. Okay, and that kind of gets into the slope and the intercept. And there's another one that says, here's all the stuff you need. And maybe this doesn't have quite, well, they have some net profit for the poor old developers and all of that stuff. Now, I'm gonna stop for a minute and go to the Excel. So what we're going to do, I'm going to try to do, is I made a battery example. And we're going to try to really, for once and for all, I'm going to try to do this. I'm going to try to understand, and I might have to make some breaks here. I'm going to try to understand what the true cost of a battery is compared to solar. And this is going to integrate analysis of the cost of the batteries, how much duration do you really need for the batteries, things like the round trip efficiency, and I'm going to go through some more slides on this. And this, in this example, I'm going to really try to focus much more on, number one, keeping it as simple as I possibly can, to avoid the kind of mistakes I've made and the BS I might have told you. We're going to include things like degradation of the battery. There are all sorts of factors to include in this analysis, and let's see what the cost of a solar project is. And I'm going to redo this, but we're going to go down and get the LCOE, and I've done something totally wrong. I'm going to come back and redo that, and then we're going to put the battery together with the solar, and we can put the solar plus battery or solar plus thermal. And let's try to, for once, everybody wants the batteries to work totally. No question about it. But let's use this as an example of really how to make an analysis. Okay, and it's going to depend on a whole host of many different variables, ranging from the characteristics of the batteries to the cost of the thermal to the cost of the fuel for the thermal, so many things. Now, to get started, before we get into some of the characteristics, let's go through the loads. So what I did, and I want to try to explain this, I put a counter from 1 to 24. Remember the elephant in the room, and that is there is doing a one-day analysis, doesn't account for cloud cover suddenly coming and all of that. And then I put in a normal distribution. And when I put in a normal distribution I put a standard deviation of 3, and the mean occurs right at 12 noon. And you just put equal norm distribution, and you put the standard deviation. I put a standard deviation of 3, and it provides 99%. So you put norm dist, and you put that in. And don't think I'm being so overly fancy with curve fitting or some other things. The normal distribution is about the simplest thing you can do. And we can create a whole host of different potential shapes. And this first shape is going to be kind of coincident with the solar, because the solar will tend to produce more capacity right at 12 noon. Now you could adjust it all differently. You could say, oh no, the load is more concentrated at 3 in the afternoon, and you could kind of move this 12 around and move some of the other numbers around, and that's exactly what I've done. And then I've said, okay, we can just use a flatter load distribution where it's not quite flat, but it's kind of flat. Maybe I'll make this 8. And then you can see that this is changing. By the way, I just learned something. If you go to the sparkline, sometimes I had some real problems with this adjusting the axis. I made the same axis for all of them, and that really improved the way those sparklines work. Of course, you go to insert and you go to sparkline somewhere here to do all of that. Okay. So we've got some different shapes, and then as I do so often, and I notice that people who are very bureaucratic about making models will even use those. I'm just making it. We'll even. Oh, I should do it maybe. How about let's make it 6. Even if you're very bureaucratic about making your models and you don't like these drop down boxes, the drop down boxes for different scenarios can really, I think, help. And maybe I need to make it a little longer. And so what we're going to do is we're going to see the cost of the batteries compared to the cost of alternatives, all thermal, solar plus thermal, all of these things. And we want to do this in a fair way. And what I suggest doing is starting with kind of the simplest thing we can do. And I thought it was the simplest thing, and I was kind of wrong about that. And the different shapes will give us different durations. And what I did in some of these ones is I put a different kind of, I tricked it and said, instead of going from 1 to 24, let's take some and put some 1s and put some really high loads right in the night time when you're going to use your lights. Okay, so we can put all sorts of different load shapes in and start really doing our evaluation of what happens to the cost when we do these different cases. Now, I'm a little afraid of this, and I might have to. I think I'm probably going to have to do this in 2 parts. Okay, perhaps that's fine. And the next thing we're going to do is so then we can just put this load thing in. And I really did. I hope I didn't put a crappy version of this generic macros on my website. But I might have, and then people get all pissed off at me. That's not a swear word. Okay. Then I put in all the loads, okay, and then I put in all the loads, and we can either have flat loads, or we can have shaped loads, okay, and it's the same sort of thing. I put the little differences in, and we start with our load, and I said, okay, we're going to take this shape that we used, and maybe I should have, I did this kind of badly. We should be kind of explicit about what shape we used, and we should then, this is why it might take a little bit longer, and we should put from our loads, let's show the shape we have. And whenever we do something like this, we can say, well, the average is just the average of all of these, and it should be the same, I hope, no matter what we're doing. And I'm looking at this average right here. Okay, no matter what kind of shape we're doing, the average amount we use during the day is the same. And this is just a percent. So I'm going to put little units. I don't know why I put them after here. And these are some inputs, so I'm going to leave that blank. And then we can put the maximum we use. And this is going to be a big deal. And right now, the maximum is higher than average. If we have a very, very flat load, the maximum equals the average, and you can compute a load factor like you would compute a capacity factor and say that we take the load factor is the maximum, and let's put a perfectly flat load. And then the load factor is 100%, which means the average is exactly the same as the maximum, and we can put a sum. And because I'm getting kind of what should I say, a little bit. I've done this wrong before. Let me just say it that way, okay? And then if we take and maybe I'm doing it wrong again. It's totally not only possible but probable. And then when we take our load, that's not very complicated. We're going to stick it in. Now, I tell people this load could be for the city of New York. This could be for the city of London, Paris, better. Oh, that's even better. And that's where we'll start. And any kind of old-fashioned electricity analysis would start with that. And if you whoops, I can't get the top one. You notice what I'm trying to do is I'm trying to get the answer. And frankly, I don't know the answer of just how cost effective batteries will be with a whole host of different assumptions. And the next thing we need to do is put some solar pattern in here. Now, what I did here is because really my favorite client. I have to say they've been wonderful for me for so many years in Malaysia. I get to, and what's this going on here? I get to, why I seem to have stopped it. I went to the EU website and I downloaded solar loads for Malaysia. And when I downloaded the solar loads for Malaysia, I downloaded the kind of hourly loads from 2005 to 2016. That's what's on there. Who cares if it's, some people say, oh no, that's the year Trump was elected. Oh, who cares? Okay, well, I care. But this is the point of access energy. Okay, and remember, the final energy you have is not the point of access energy. You might have a performance ratio, and that means that you're going to get less load delivered from the grid than is actually produced. That you can call that the in-plane radiation. Now, it's totally possible, it's probable that if you have hotter times during the day, you'll get a lower performance ratio. And I did a simplistic kind of thing where I just took the loads, and then I said, okay, we're going to take, in this case, the load is for the 22nd of, I'll put it the 23rd. That was my father's birthday. The 23rd of May, 2008. Right before the financial crisis. That was the load. And it just goes downstairs, picks the load, puts the point of access power. Now that's relative to STC. It's relative to standard testing condition. I went through all that in another video, so I'm not going to do that again. And you can then compute the capacity factor as this one divided by the standard test, the 1,000 for standard testing condition. And then you can multiply it by the performance ratio. Now, the only question is, how do I get this? So if I change this to the 24th of May, or the 25th of May, we get a different number. Now, what I want to do is to be able to kind of do this a little more quickly. So I'm gonna put for the let's. Oh no! See, I'm struggling. I put up here that we might take the 24th of May, 2008, and then I just changed the year, I guess. I'm gonna let's leave the let's put the. Okay, how about this? We'll kind of cheat on this one. Now, what I do here, let me just finish this discussion. So once you put the year and the month and the day, and you just make a date function. That's not hard. And don't forget to press Shift Control F3, 3, not F3. Shift Control 3 to get the date formatted, and then you use a match. Make sure it's, and you don't, the thing you don't do, you put equal match. I can do this. And then you click and you compare it to all the dates. How easy is that? And then you put (0) to make sure it gets the first hour of the day in that column. And if you don't believe me, you're going to make me find, whoops, oh, you're going to make me find A38, let's put A5, A38512. And you can see, there it is. It's right. It's the first time it found it. Not a big deal, but it's a helpful little thing to do. And then you take this number and you go down the next 24 hours. And then once you go down it, you use the index function on the whole column. Please use the whole column or the whole row. You probably won't. But if you start pressing F4, it's going to take about 3 times as long. So there's our loads. And perhaps, why don't I just, let's leave the day kind of as the middle of the month. Who knows if this is a weekend day or not. Maybe I should. I don't think the the sun sits there and worries about whether it's a Sunday or a different day to decide how much sun it should put there, or whoever decides that. Certainly not me or you. Okay, so maybe we can change the date and get a different solar pattern. And this is starting to be our elephant in the room problem that we can, when we're honest about the solar, we can get very different numbers. Now I have been working a little in Abu Dhabi, I guess, and if we, I hope this is this is our battery slides, not our hydrogen slides. And when I discuss ancillary services, so I'm bouncing around a little bit, so that man who said, you can't keep focused, you idiot. Well, this is Paris. Okay, I'm pretty sure this is Paris, and this is a day in Paris where we suddenly got a cloud cover coming in. Okay, and this was, I show it with I didn't put series 1 and 2. That's with and without tracking. Yeah, here at least I put that. It was with and without tracking. And this is where I would do that same graph that we just did. But when I would do that same graph that we just did, I'd do it for, instead of 24 hours, I do it for 168 hours. That's how many hours are in a week. I think 7 days times 24 hours times, that's it. Okay. I have to think about that one. And then this in northern Nigeria or the desert or in Abu Dhabi, the loads are going to be much more simple, stable. Here is our 1000 STC, and we have sometimes there's a little bit higher, and this one it's the same kind of issue. There are a few hours where you get more, but after you put the performance ratio in, you're not going to get more. Okay, and in this case, you need some batteries just to back up because you suddenly go down. You know, maybe you don't need batteries right here because you're going to have a cloudy day anyway, but if you suddenly have cloud covers here, you've got to get enough storage just to get it back. That's our 15-minute storage issue, and that's not the issue I'm addressing right now. I'm addressing issues, and we can pretend the loads are something like this, which are pretty stable, and if you have every day that's about the same, what's the true cost of storage for something like this? So let's go back and let's find a solar pattern. Well, you know, maybe there's a lot of rain in that. Whoops. Oh, that last one was pretty good. And we can try a different year, and I'm looking at this thing here. Ooh, that wasn't any good. I'm trying to find a fairly, that's a pretty stable number, isn't it? Okay, so you can go and get the a pattern of the solar factor, and then what I do is just, you know, if you're, please, oh, I'm going to start crying about this. I really am. There's this guy I'm working with who thinks he's, I'm not going to criticize. I'm so good at Excel. I'm so good at mulling, blah, 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 but my formulas are so damn long. I'm not supposed to swear. Shit. And then I'm sorry. And then you press the control and square bracket and you find out where the numbers come from. And if you can't easily find numbers really, really easily with square bracket and F5, something is wrong. And I would say, start over again and give me a mall I can understand. Now, when we do this solar pattern, we got to be a little bit careful. If I compute the load factor, which is one of the mistakes I kept making before, which says take the average divided by the maximum, well, that's not quite right. The real, these capacity factors, and you can argue, oh, they're wrong, they're still wrong, and you'd kind of be right about that. You certainly would. But when we look at the hourly solar, I put this performance ratio. So if I put a 75% performance ratio, for example, in here, then I get this is the capacity factor, which is simply the average of the capacity factors over the day. I'll put it back to 80%, and of course this should have been maybe, you know, if you use this thing here, you can then reset everything, and this time I'm not going to put a top color in. And if you're having problems with this, I bet you nobody uses this. It's so sad. But I use it. I'm going to find one person. There's one person who uses it. Okay, and this, oh good, these are the inputs, and so you can see that this is an input. Okay, you could have done that 8 different ways, but there we go. You notice I'm pressing Control Tab. You don't notice that because you can't see me, but I am pressing Control Tab, and I've got a little macro to make that work, and you can look at the blah, 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 other stuff. Okay, so that's our solar, and the big deal is that this load factor and this capacity factor are not the same, and I'm not sure if we divide it. It's not quite the performance ratio because we get different, because we never hit the 1000 STC in some hours. So you got to be very careful. And then now if we're going to make, let's use our flat load case. Let's use our very flat case, or we can use our perfectly flat case. And maybe, you know, of course, if you want to go and change this, you could put perfectly flat. When you do this, then let's see, in this case, I need to get 1,000. This is really, I gotta be careful. This is megawatt hours. This maximum is megawatts. And it's always a little confusing to me. Megawatts are an instant, so whether that's a megawatt hour or not is okay. All right, within the hour you could have some fluctuations. Yes, we know that, but we have to at least get some kind of framework to make this possible, to get some understanding of it. Okay, so we have 1,000 megawatts. Now I need to get 1,000 megawatts of solar. Now I'm going to put no round trip RTE, round trip efficiency. I'm going to assume we have this perfect kind of battery where every single tiny bit of energy we put in, we get right back out. Okay, that's not the case, but we're going to assume that because we're going to try to really understand things. At least I am. And I'm making a video while I am trying to get a handle on some of these issues. Okay, and then I had to write this stupid formula down. Capacity factor is average divided by maximum capacity. If you have a plane, it's the number of the seats that are occupied divided by the total seats. And every time you have a plane ride, you should think, oh, what's the capacity factor of this plane ride? But then you can say, no, this plane's going to be on the ground for a while, so I should take the average of over the whole day, including the nighttime when the plane is not on the ground, and it's kind of just like solar. And then we can see, well, okay, that means that if I go the other way around, I can figure out how much solar capacity do I need to meet this average load. So I take the average load up here and divide it by the capacity factor, and that's a painful thing to do, and that's one of the mistakes I've been making, and that gives me the total amount of capacity for solar that I need, and it's not the average load or anything like that or something like it. It depends on the capacity factor of the solar project. Okay, and maybe this is a little theoretical, and it is, but we really want to understand the theory of how much it's such an important issue in the world, whether you can store the electricity and get the same amount out. It's just enormous. So then all we do is we take our capacity, this 171, I hope, and we multiply it by the, I put the capacity right here. I just spread it over our 24 hours and I put it right here. Okay, and then I say, well, here's the amount of solar production we're getting. Okay, and there we have it. By the way, I've been working on and off peak energy and other things, trying to get that in a simplified framework. Now, the next thing we do, which is not so complicated, it really isn't. We say, okay, let's take this load we have and compare it to the solar production. And we have to take things, if we have more load than the production, we just use a concept from cash flow waterfalls and say, this is the amount we can store in our battery. Now, we have to meet this load. And so we have to meet this load. So we take away the amount of load we have. This is the total we can get from the sun minus this. And if this is negative, stop. Don't make the calculation. You can't store anything. It's only positive. So this is how much we're storing during a hypothetical one single day. Again, the elephant in the room is we have different solar patterns over different days and all the rest of it. But my position right now, and I'm going to stick to it, is that let's get it right for one day. And once we get it right for one day, we can put it for 1 month and 1 year or whatever, and we can put in different solar patterns and we can do whatever we would like. But let's start with that. And then we go the other way and say, well, when are we going to dispense our solar? And that's whenever the load we need is greater than the solar power. So in this case, we have 41 versus no solar power. So we have to dispense it all. So we're dispensing it all here, and then we're charging it. And one of the problems I kept kind of running into, and notice this, why does this happen? I'm kind of muffed by this one. Alt O C row. Alt O row and hide. Shift Alt right arrow. I'm hiding the see that what I was muffed by is why this disappeared. This our little, and I notice that happens a lot when I redo the things. And now what? I can't hide it anymore. What's going on now? And now I seem to be stuck. Just a minute. Okay, I hope I've got my little thing resolved now. If we put different shapes in for our load, and if our load looks something like the solar power, here's a kind of interesting thing. Here's how much solar power we produce. It's the 1000. That's good. Without any round trip efficiency. Here we have a little bit of solar capacity that's extra, and we need to put that in a battery, and we can immediately see how large a battery we need. Now, I'm hardly started with this. If it's a completely flat load, I need a bigger battery. If it's very flat, it's telling me how much extra do we need to store and then take out. And then I have something wrong here. Okay. And this is driving me completely bonkers right now. I had to get another line here because we need one more calculation. The final calculation we really need is how much load do we actually serve from the solar project itself without having to dispense the solar. So let's try our little experiments with different load shapes again. And in this case, I served 894 of our 1000 load from the solar, and I have to get the remainder from the battery because we have this kind of, I would call this a coincident load shape. And I've gone through that before. But if it's very flat, then we have to serve 559 from our solar. And then if we have this off-peak number 2, then we have to get most of it from the battery because our load is mainly off-peak, and we need more of a battery. And this is where I said this duration kind of issue is going to come in. It's the megawatt hours we need relative to the size of the putting things in the battery. And we can divide it out and call it hours. But to call it duration of the batteries is a little bit off. Okay, so we get the amount we need from our soul. Maybe the reason it's not working is I closed this sheet off when I was working with this in a class. Okay, so finally now, and I'm gonna this will be a natural stopping point for me. I'm gonna stop after I've gone through this little balance calculation, And the rest, it looks like it's going to be a real pain, but it's not, I don't think. The problem is if I'm doing a 1-day analysis, I go crazy with this. I have to know, does the battery have any storage in there already? Does it have anything in there already or not? And I'm going to assume the battery is empty. It's like your phone. You've left your phone on at night, like I do sometimes, or whatever, and okay. And then you have to figure out the first at what time you're going to begin the charge. And this time, so we're going to begin to make our charge the first time that the solar is greater than the amount of load we need. So the first time that this is equal to 0 and the earlier one is not equal to 0. And hopefully that's not going to be at 1 in the morning. Well, I doubt it will be. And because it's normally not very sunny at 1 in the morning. And when we do that, then we're going to start charging it, and we're going to keep charging it, and then we're going to discharge it. And we need to make this in chronological order so we can keep track of our balance that's in the battery. And if you kind of remember this sort of stuff we've done, I used to be so afraid of going up and down PowerPoint slides, and it's really not that bad, is it? We need to know this in terms of kilowatt hours and this in terms of kilowatts. Is that the one I was looking for? I think. You know, all of this business of how much you need, or this one, what's the duration? How many kilowatt hours do we need relative to the kilowatts? Okay, so let's keep going. I'm still making the video. I had to check. So I go through, and this is just a little bit of painful Excel. I don't want to really show it to you all, but I make a little and statement that says, let's take I had to make it even fancier in case there were two numbers. I said, well, this thing, this thing has to be greater than 0, so let's go up here. This thing has to be greater than 0, and this thing, the one before, has to be equal to 0, and it's the first time we've started it, just in case you have two little things that go up and down, and that would be possible. Let me see, perhaps in this one, it might be possible that do I have the this is on, okay. Do we have two ones here? Maybe not. Let me just try one more and see if we can find one that has two different switches going around, and maybe I can't find that, which is very good. Okay, and then you use a little match function again, or no, you don't. I use the XLOOKUP here. And I said, well, let's find out when we hit the first one. And that's why if we have two number ones, we got to be careful. I want to take the first time we store the battery, and I suppose it would be possible to suck it all out and get a negative storage balance. But we're just going to find the first one and just get the hour. So when I did this XLOOKUP, I said look up on this hour. So the 8 up here is this hour number 8. That's when we're first going to store it. And then I go crazy with the recounting. I start with the 8, and there are other ways to do this. And then I say, well, let's go, and if we hit 24, we've got to start all over. I do it different every time I do it, but here we hit the midnight, and then we're starting over. And in that way, we organize things so we're first storing it, and then we're dispensing it. And I better put my flat load in Okay, and I'm going to pause. Okay, so I'm a little embarrassed. This is just such a pain. I have to use the match function and find the column number. I don't have to, but that's the way I do it. I use the match function, a little bit of pain. I go up to the hour number 9, and then I just click on this row number 3, and it gives me the column number. So when we hit the hour number 9, if we would do a equal column, that is column number 19. Okay, and then I go up to 19, and then it goes around, and as soon as we hit number 24, we go back to column 11, and then once I do that, and that's what I was freaking out about just now, I use the index function, and I say, well, how much do we store? Starting in the first storage, this is how much we put in. And then how much do we dispense? And notice the storage and the dispense are the same. Now that's not going to happen if we put in our round trip efficiency, if we have to put more in than we take out. But for now, I'm going to just get this straight. Just get this designed. Just get a simple one-day analysis so you can really proceed. Now, when we put our balance together, for me, this is like putting a debt balance together. And when you really think about it, the debt balance accumulates and it changes. And the changes are megawatts or kilowatts, but the accumulation is megawatt hours. And all we do is put an opening balance in, and we put the amount we put into the battery in, and then we take it out. And then we've got something more interesting, which is the accumulation of the storage. And that's what we really need. And then we just take the maximum of that balance, and that's how much we have. Now, if we want to measure the capacity that we either have to put into the battery or take out, remember that's like how fast your a phone charges or discharges. We can take the maximum of this, and that's our battery capacity. Now, perhaps somebody will dispute me. I think this one's very clear, and this one that's how you that's kind of what the definition of the capacity is, and that gives us our duration, which is not really in hours. It's just the dividing. And if we would put our more coincident load, we only need a battery of 2.2 hours. If it's more flat, 6 hours. If it's very flat, 6 hours. And this is where the battery starts to get kind of more expensive. And this is maybe a little bit smaller of an elephant in the room. If we put non-coincident load, we need that. Now, a battery can be very, very, very effective and cost effective for the ancillary services, for the sudden changes in demand. But when we're looking at a different kind of load shapes, we get very different answers. And then what did I have here? So now, solar capacity for storage. What the heck is this? Oh, this is because, well, I'm going to come back to that one. The solar capacity is we have how much solar capacity we're putting in, and we have to consider that. And then we have the fundamental characteristics of the battery, and we have this. And finally, what I was trying to do was make some graphs of it all, and we have some of the solar that's there to meet the load, and some of it's not. And we can eventually now say, okay, let's just put solar in. Screw the rest of it. Let's just put let's just put solar in. Now, if we only put solar in, we're not going to put this much solar in. Perhaps we're only going to put in solar to meet the load. Why would you put in extra solar capacity? A thermal plant can't suck out the solar capacity and use it for fuel. So you're going to have to put in less solar capacity if we just do thermal plus solar capacity. And we'll get into that one later. But let's really kind of focus on this pure, nice, totally pure case. And let's see if what the total levelized cost of storage really is in these alternative scenarios. Now, I'm not going to keep going on because my video is so much too long already. I can't imagine. If you've made it to this end, could you send me an email? Because I can't believe you would have listened to this whole thing. So I'm going to stop the video right now.